Hello and welcome to this fifth session. Last time we were looking at ionization energy mainly, but at the end we looked at atomic radii, and that's because these radii are really explained in a very similar way to how we explain ionization energy. So for example, across the period going from left to right, as the outer electrons experience a greater nuclear charge, then they're pulled in closer to the nucleus, and so the radius shrinks of the atom. And likewise going down a group, as we're filling electrons that are further from the nucleus, or as the electrons are filling shells further from the nucleus, then the radius of the atom is increasing there. Now we're going to move on from atomic radii to ionic radii. So we have some data on this graph, slightly more complicated graph with sort of some multiple data points for some elements. And it's really all about the charges on the ions. So looking at the atomic number on the x-axis, again this is reflecting something like our group number if we subtract 10, but this time of course we're considering the ion, so the group 1 element will form a 1 plus ion, the group 2 element 12 a 2 plus ion, 3 element 13 a 3 plus ion, and so just as the atoms would shrink going from left to right across the period, of course the positive ions shrink as well, in fact even more so, because you've got these an additional loss of electrons, and so you have a greater proton to electron ratio, a higher net charge, and so an even greater shrinkage. So the positive ions there, they're all isoelectronic because they're all emptying out their outer shell to give you the neon configuration below. So really we're just adding more protons to the nucleus with these ions, causing this shrinkage, the extra attraction of the outer electrons to the nucleus. So that's what we see starting from the left and the downward trend. Right at the top right of the diagram, we actually have some negative ions. And so on the right hand side of the periodic table, in groups 5, 6 and 7, so these are atomic numbers 15, 16 and 17 there, we've got phosphorus, sulfur and chlorine, and these elements can fill their outer shells to form negative ions. And so we see that these negative ions up at the top right there, they're much larger than the positive ions. And so we can think of this in terms of the ratio of electrons to protons being the other way around, favouring the electrons. And also, of course, they have filled their third shell rather than having emptied their third shell, which is what we're seeing in the positive ions. So they've got a whole extra shell of electrons. So of course you'd expect the ion to be larger for that reason as well. And now just looking in a bit more detail at these elements on the right hand side, so phosphorus, sulfur and chlorine, we've got the largest value and the smallest value effectively of their oxidation states. So plus 5, plus 6 and plus 7 oxidation states there are when the atom is using up all of its electrons in bonding. So it's rather an exaggeration to think of these as simple ions. You're not going to get just, a Cl7 plus ion as if it's just a completely isolated entity. But really, it's actually going to be engaged in some kind of covalent bonding, but it's going to be bonded to an atom which has taken most of the electron density for itself. So it's not quite a 7 plus ion, but we can kind of approximate it that way in this kind of ion, in a sort of crude ionic model. And so certainly we see this quite nice trend across the period. So looking at the lower dots on the graph, they are going down the whole way for this isoelectronic series where all the atoms are essentially emptying their outer shell, just leaving that neon configuration, as I said, with an increasing number of protons each time. And then up there at the top right with our P3 minus, S2 minus and Cl minus, of course they're all isoelectronic as well. They've all filled their outer shell, the third shell, And following a very similar kind of argument, we'd expect P3- to be the largest one, because of those three, it's got the fewest number of protons in the nucleus, trying to hold in those 3 shells worth of electrons, or going up to argon at least. And then as you add another proton to the nucleus, they gradually shrink down. Of course, the x-axis stops at chlorine there, because after chlorine, where you have argon, of course argon doesn't form any ions, so ionic radius isn't relevant for argon. Now this takes us on to our next idea, which is electronegativity. And again, this follows on very nicely from our earlier discussions of ionization energy and atomic radius. And it does come with a bit of a health warning, because there are multiple ways of looking at electronegativity, and there are actually multiple scales of measuring it. So it tends to be a slightly kind of nebulous idea. And so what I'm going to do here for the time being is just take one particular approach, the so-called Pauling approach, with his Pauling scale. And in this particular approach, it's all about looking at bonding electron pairs. So of course we're assuming therefore that the atom is forming covalent bonds. And actually it's for that reason, when you look at the graphs on this slide, again there's no noble gas. So in this particular way of looking at electronegativity, where it's really all about chemical bonds, obviously we're disqualifying elements that don't form chemical bonds. So it's really to do with how the nucleus attracts the bonding pair of electrons. And so, not surprisingly, it's quite closely related to ionization energy in a way, because with ionization energy, that's really all about the nucleus exciting electrons in the valence shell. But in this case, rather than just the valence shell electrons of the atom being a bonding pair, it's also involving an electron from another atom, which has its electron in a shared pair bond. And that's why in this text here, I also make reference to electron affinity. So electron affinity is kind of the opposite to ionization energy. So in ionization energy, an atom loses an electron to become a 1+ ion, but with electron affinity, an atom will gain an electron to become a 1- ion. So if you think about it, there's an additional electron involved in forming a bonding pair, and so again electron affinity has some kind of relation to this. We'll look at electron affinity in more detail later on. Now, rather like ionization energy, we see these patterns emerge where the electronegativity increases from left to right across a period, and it decreases going down a group. So that's why it's quite sort of convenient to think about this concept just after having looked at ionization energy, as they're quite related. Now, in my opinion, electronegativity is really grossly overused in chemistry to explain things. And so, as I said before, it's a slightly vague concept with lots of different approaches to talking about it. And so I'm not a great fan really of referring to electronegativity very often, but there is one circumstance where electronegativity is just the right concept to describe something, and this is to do with so-called dipoles in covalent bonds. And so in a covalent bond there's a shared pair of electrons. Now that electron pair being shared by 2 atoms, that pair of electrons is being pulled by both nuclei. That's to say both atoms which are sharing an electron to form that bond. The nuclei of both of those atoms are pulling on that shared pair, and that pull is essentially the chemical bond holding the atoms together. And so the point about this electronegativity, which actually very nicely fits this particular scale, it's to do with that kind of tug of war between these 2 atoms. And so a more electronegative atom, since we're defining it here in terms of the nuclear attraction to that bonding pair of electrons, a more electronegative atom is going to kind of win out in that competition over the bonding pair. And so the bonding pair will get kind of pulled preferentially in the direction of the more electronegative atom. And so this ends up causing a kind of uneven distribution of the electrons in the bond. And then that uneven distribution of electron charge means that you end up with a kind of lopsided charge density on the bond. And so the more electronegative atom, which is kind of hogging the bonding electrons a bit, with more electron density around it, picks up this partial negative charge. And this is where the Greek letter delta comes in, that we refer to on the sheet there. It's got a delta minus charge, meaning it's just got a fraction more of the electron density around it. So this is a bit different to the charges we met before when we're looking at ionic radius. They were whole charges, like 1 plus 2 plus 3 plus 1 minus 2 minus 3 minus, where an electron is simply lost or gained. But now we're looking in this electronegativity concept, we're not looking at whole electrons leaving or being gained by an atom, but rather just slight shifts in that cloud of electron density. So we think about electrons as being in orbitals, and so that's like a region of a sort of diffuse region of space where we find the electron density. Well, that diffuse region of space can just be kind of pulled in slightly more towards one atom or the other. And so if it will be pulled in a bit more towards the more electronegative atom, which will gain this very slight partial negative charge, delta minus. So actually you meet the symbol, this lowercase Greek delta, you meet this in maths as well to depict a very small change in a quantity. So it's the same idea. Likewise, the less electronegative atom, which might sometimes be called more electropositive, the less electronegative atom is kind of losing out on the electron density in the chemical bond, and so that slight shortfall it has in its electron density arises in a partial positive charge called a delta plus. Now, of course, assuming it's say a simple diatomic molecule, the overall molecule must be electrically neutral if they're the same number of electrons as protons. So if you have a delta minus on one end, there'd have to be a delta plus on the other end to have overall electrical neutrality. And so this takes us onto bond dipoles, and I thought it was worth exploring this just a little bit further. So we have these partial charges each end of a bond where the atoms have different electronegativity, and this is often described in terms of polarity. So if a bond has a dipole, it may be associated with a molecule that we call polar, for example. And on the right hand side of this slide we see some different cases of this kind of thing, and we're just going to have a quick look through them and we can relate this to electronegativity. And so we begin with a kind of trivial case where if the two atoms bonded together are of the same element, so there's the same electronegativity, there's then no reason for any kind of imbalance in the electron density. And so for this reason we would say there is no dipole, and that bond and that molecule would be called nonpolar. Now in the next case there, HF, we've got a significant difference in the electronegativity. In fact, fluorine here is the most electronegative element in the periodic table. So if you think about it, if electronegativity increases from left to right across a period, and if it increases when you go up a group, you would expect the top right hand corner of the periodic table to have the most electronegative elements, and likewise the bottom left hand corner to have the least electronegative elements. Now of course right in the very top right hand corner of the periodic table, of course we've got helium and neon up there, but of course the way we're looking at electronegativity in terms of bonding pairs of electrons, helium and neon are kind of disqualified, and so that leaves fluorine as our most electronegative element. And so for example, where a fluorine atom is bonded to hydrogen, there's a really significant difference in electronegativity there. And so I've suggested where you have a some kind of significant difference in electronegativity, perhaps greater than a half, let's say, on our Pauling scale, then you would refer to the chemical bond as being a polar bond. And so you could write a delta plus on the H and a delta minus on the F, for example. But we've got an interesting one coming up here with carbon dioxide, because the carbon and the oxygen atoms, there is a significant difference in electronegativity. And so any one of those two double bonds that we see, either of the C double bond O's, in itself could be regarded as a polar bond. But really, when we're looking at molecular properties, the important quantity is the molecular dipole, the overall dipole. And it turns out that we need to sum up, if a molecule has got multiple bonds, multiple dipoles, let's say, we have to sum them up. And actually they sum up rather like, well, it's a vector, a dipole. And so rather like, say, in physics, you might have two different forces in action, and you would do a vector addition of those forces to get the overall force. Likewise, we would have a vector addition of the two dipoles in a carbon dioxide molecule, and because the molecule is linear there and symmetrical, the dipoles would exactly cancel out. So actually, carbon dioxide is referred to as a non-polar molecule, despite the fact you could argue its individual bonds are polar, because the molecular property is what happens, is what you're really describing, the sum of the dipoles. And the dipoles have this direction as well as their magnitude, like a vector, and so they can cancel out. Quite an interesting example at the end here is water. So of course water also has two polar bonds, rather like carbon dioxide, but it so happens that the shape of water is not linear like carbon dioxide. And for that reason, the dipoles don't completely cancel. And curiously, thinking of them as vectors, there is a certain amount of cancellation. If you think about a kind of horizontal axis, then the horizontal components of those dipoles would cancel, but the vertical components would actually add together. And so you can see in the diagram the red arrow with a little mu on top of it, that represents a net dipole. So actually, slightly unfortunately, I think that arrow ought to be pointing down. You normally have arrows pointing towards the negative end of a dipole. And so this is why we describe water as a polar molecule, but carbon dioxide as a non-polar molecule. Now, the concept of electronegativity also has a bearing on oxidation number and is relevant too with our earlier discussion of ionic radii. So just thinking back to ionic radii, normally we think about it in the very simple case of a simple ionic compound made of simple ions, like for example sodium plus and Cl minus, when we consider ionic radii. But of course, remember when we looked at that diagram, we also saw there were some very large ionic radii quoted for non-metals. Of course, normally we think of non-metals as forming a negative ion, for example sulfur going to sulfide, S2-. But in fact, these non-metals can also adopt, as we saw before, some very highly positive oxidation numbers. And in fact, as we see, electronegativity is going to have some slight connection to this. And so looking now at oxidation numbers greater than 4. So we said back then that when we looked at ionic radii with these very high positive values, +5, +6, +7, these weren't really simple ions. Actually, these atoms were involved in polar covalent bonds. And of course, we've just been talking about polar covalent bonds. And so a couple of things to say about this. So first of all, with these very high oxidation numbers, what we're really looking at is a so-called expanded octet. So for example, phosphorus, if phosphorus is using all 5 of its valence electrons in bonding, in polar covalent bonding, there'd be a total, once each of those 5 has been shared with electrons from another atom, there'd be 10 electrons altogether in its outer shell, so hypervalent, exceeding its octet. Likewise with sulfur, if all 6 of its electrons are being used, there'd be a total of 12 electrons once they're shared, again hypervalent, expanding its octet. And in the case of chlorine, if all 7 were used, that'd be 14 electrons altogether. And so what really drives these atoms to use all of their electrons and to expand their octets? And in fact, what it will be in practice, it will be bonding with a very electronegative atom, an atom that's much more electronegative than it is. And in that case, the electronegative atom, as it were, really kind of yanks on those electrons, because we think about electronegativity as being an atom's, as it were, hold on a bonding pair of electrons. And so it tends to be elements like oxygen and fluorine, the two most electronegative elements, that often drive nonmetals to form these very high oxidation numbers, and hence getting these very small ionic radii being quoted. And so they draw out these electrons into bonds, and these are polar covalent bonds, as I say. And because a very electronegative atom is required to expand the octets in this way, that is why necessarily the nonmetal bonding to the oxygen or the fluorine is going to have a positive rather than a negative oxidation number. And it's because the sign of the oxidation number is going to follow the relative electronegativity. So when two atoms are bonded, the more electronegative atom is going to be the one that takes the negative oxidation number when we're looking at a polar covalent bond. And so just making the point here then that when we've got covalent bonding between different elements with different electronegativities, the number of electrons involved in bonding is going to give you the magnitude of the oxidation number, and the sign of the oxidation number then is then determined by the relative electronegativity, the more electronegative element having the negative oxidation number. And so then, as you can see by this logic, fluorine, which is the most electronegative element, is always going to have a negative oxidation number in compounds, because there's nothing more electronegative than fluorine for it to bond with. The only time it's not negative would be in the fluorine molecule, the FF molecule, when it's bonded to itself, and that would be a pure covalent bond, and it's elemental, so it'd be oxidation state 0. And I've just put up a few interhalogen compounds here to make another point. So you see with these interhalogen compounds, I've got these 3 interhalogen compounds up there. So in each of these cases we've got a diatomic molecule, like we see in halogens normally, a diatomic molecule, and but different halogens. And so we would assign, so all the oxidation numbers here will have a magnitude of 1, and so in the top one, this chlorine monofluoride, in this case the fluorine would be -1 and the chlorine will be +1. Chlorine's not as electronegative as the fluorine. Likewise, bromine monochloride, BrCl, bromine would be +1, chlorine more electronegative, -1. And again, iodine monobromide, IBr, iodine would be +1, and the Br, which is more electronegative, would be -1, because of course the electronegativity decreases as you go down the group. And this has a bearing on the naming as well. Actually, if you think about when you name compounds, you start off, I mean, for example, in a simple ionic compound like sodium chloride, the first word of the name is the cation, the second word is the anion. Likewise, when you're looking at covalent compounds, the first word of the name is going to relate to the positive oxidation number atom, and then the second word to the negative oxidation number atom. So that's why, for example, in these interhalogen compounds, you would call it iodine monobromide rather than the other way around. You wouldn't say bromine monoiodide. And this is the iodine being relatively electropositive. It's at the positive end of the dipole, and so a bit like metals, which are positive, go first in the name in a salt. Likewise, in this kind of covalent compound, we'd start with the less electronegative atom and then go on to the more electronegative atom. And so you may not have met these before, these interhalogen compounds. One quite interesting thing about them is their appearance. Actually, their appearance tends to be the kind of average of the elements. So you might be able to guess which one this is. So you look at those 3 up there, and then look at the colour of that compound in the bottle there, and you might be able to make a judgment looking at those, which one it's likely to be. Now, another thing I wanted to say with electronegativity is to relate it to the percentage ionic character, because I think, as we've established now, ionic and covalent, it's not just a black and white thing. We can talk about pure covalent, certainly. If you've got two atoms that are identical, so they've got absolutely the same electronegativity, and so in this example I've got up here in the hydrogen molecule, H2, two identical atoms, obviously the same electronegativity, clearly there can be no dipole. There's no reason for the electron distribution to be at one end or the other. It's going to be equally shared between the two hydrogen atoms. So with these so-called homonuclear diatomics, when you've got two atoms of the same element bonded to each other, H2, O2, N2, you could say that bonding, if you like, is absolutely non-polar. So you could say that's covalent bonding. But then, of course, when it comes to ionic bonding, we're going to see a very large difference in electronegativity to give you really ionic character. So again, you might ask yourself, what would be the best possible example of an ionic compound using this idea of difference in electronegativity? And so it should really be between the most electropositive element and the most electronegative element, and that will give you the best, as it were, electron transfer between the two. And since electronegativity increases from left to right across a period, and electronegativity increases up a group, it should follow then that the element, as it were, at the bottom left of the periodic table, cesium, bonding with the element, as it were, at the top right of the periodic table, forgetting about the noble gases, which should be fluorine. Cesium fluoride, therefore, should be our most ionic compound with our greatest difference in electronegativity. But of course, there's going to be like a whole scale, a whole continuum there in electronegativity. We can have small, medium and large differences in electronegativity. And in fact, this has actually been estimated in the graph that I'm going to show you here, where on the x-axis we've got the difference in electronegativity and on the Pauling scale, and on the y-axis how this is said to correspond to the percentage ionic character. So you can see here then that if there's no difference in electronegativity, so that's two atoms of the same element, the percentage of ionic character will be 0, as we were saying before. And then right at the top, you'd expect to see cesium fluoride. As it happens, the points that are plotted here, we haven't, cesium fluoride actually will go slightly off the end of this graph. The most ionic one using this particular set of data is potassium fluoride there on the top right. And so, as you can see, as we move to the left, going from potassium fluoride to lithium fluoride, so we expect that to be a slightly smaller difference in electronegativity because lithium is not as electropositive as potassium. And then as we go further along to the left, we see now we've got aluminium fluoride, so aluminium not as electropositive as lithium. Then next when we go along, we've now changed the fluorine for a chlorine. So obviously chlorine is not as electronegative as fluorine, so that will cause a smaller difference in electronegativity compared to fluorides. Then next up we've got an iodide, so even less electronegative, so a smaller difference in electronegativity. And then the next group of compounds here we can see involve aluminium compounds. So of the 3 aluminium halides, you'd expect the aluminium chloride there to be the most ionic because you've got the greatest difference in electronegativity. It's quite curious there that the aluminium chloride there and the potassium iodide, surprisingly as well, so both of them surprisingly near to 50%. That potassium iodide actually very surprising to see that so close to 50%. Aluminium chloride, that is a little bit more odd when you look at the bonding in aluminium chloride later on. You can appreciate why that's quite borderline. And then moving down, we're getting to the much smaller differences in electronegativity, and so much more of a covalent character. And so you can see at the bottom there we're starting off with these hydrides. And so looking at these hydrides, we've got the arsenic hydride, arsine so-called, they're the hydrogen selenide, and later on we've got the hydrogen bromide. So as we move along that series, the non-metals there, the non-metal bonded to hydrogen is getting gradually more electronegative. So that means that the covalent bonding will be getting slightly more polar. So we've got this scale where you've got this sort of non-polar kind of pure covalent bonding on the far left when the difference in electronegativity is 0. And then as we move along, then we talk about the covalent bonding becoming more polar So what we really mean by that is that the covalent bonding is getting some ionic character coming into it. And so once we go past the halfway mark and we start going up to, say, lithium chloride, we would stop calling that covalent bonding with ionic character, and we'd say actually it's ionic bonding. You could say, I suppose, it's ionic bonding with a little bit of covalent character. And then as you move up to aluminium fluoride, lithium fluoride, etc., that would be ionic bonding with less and less covalent character. And then, of course, at the extreme, you got cesium fluoride, and you wouldn't really talk about that having any or scarcely any covalent character. That's certainly as ionic as you can get. So that's another quite nice application of electronegativity, because we can relate it to this is called intermediate bonding. How, in the GCSE picture, you might think of ionic and covalent bonding as just one or the other, and then when you get to sixth form, you see actually there's something of a continuum between the two. And electronegativity is quite a nice way of quantifying that continuum there by this graph. I've not spoken yet about electronegativity scales. You might have noticed on the last slide that the difference in electronegativity axis was labelled Pauling scale. So I thought I'd say a little bit about scales. Actually, there are quite a few electronegativity scales, and I just thought I'd mention the two most interesting ones. Pauling is the most famous one, the one that's normally used. It's named after Linus Pauling here in the picture. And a few notable things about him. He's the only person ever to receive 2 unshared Nobel Prizes. So that's quite remarkable. So he made many contributions to theoretical chemistry. So hybridized orbitals came from him. Obviously he did his work on electronegativity, and a lot of work on biological, organic, structural elucidation, and famously a peace activist as well. And so Pauling devised this scale, and the reason I wanted to talk a bit about his scale is it actually connects to what we were talking about before, this idea that when there's a difference in electronegativity between 2 atoms that bond together, that introduces some ionic character into the covalent bond. So he actually used this phenomenon to develop the scale. So for example, the example you can see I use here, hydrogen and fluorine, clearly the elements don't have any ionic character in their bonding, but the HF molecule will. And curiously, we see that the HF bond is quite a bit stronger than the average of the HH and the FF bond. So this is a measure of the difference in electronegativity. So he has a scale which uses bond strengths to work out electronegativity differences. And so then I guess you would just define, say, fluorine being 4, for example. You would just define the differences from some level. And so I mentioned here that he's using the average of these 2 bonds, the HH and FF. He's actually not using the arithmetic mean, he's actually using a geometric mean, which means he'll multiply the 2 together and get a square root. That just seemed to work out better for him. And I think the whole scale that we've got is based on, rather than using kilojoules per mole, using electron volts, so another unit of energy. But yeah, quite wanted to mention this because this business of the ionic character and the increasing bond strength. And one of the other scales I thought would be worth looking at is the Mulliken scale. And so in the case of Mulliken's approach, incidentally, Robert Mulliken there, not to be mixed up with Robert Millikan, both Nobel laureates. Robert Millikan was the one who did the oil drop experiment, got a Nobel Prize for physics. Robert Mulliken, he was a big developer of molecular orbital theory and got the Nobel Prize in chemistry. And so the way he looked at it was that if we're defining electronegativity to be an atom strongly attracting a bonding pair of electrons, he reasoned, then the first ionization energy should be large for an electronegative atom because it's pulling on these electrons strongly, it's not going to release them easily. And of course, because in a bonding pair of electrons you've also got an electron from another atom involved, he considered the first electron affinity. So this is kind of the opposite of ionization energy. So ionization energy would be the energy for an atom to lose an electron. Electron affinity is the energy change when an atom gains an electron. And so considering that the atom is also pulling on an electron from another atom in the bond, he used the average of the ionization energy and the electron affinity to get a measure of the electronegativity of atoms. So unlike Pauling, he's not using the difference between two atoms in defining his scale. So this is something of an absolute scale for electronegativity. And so once that's worked out, I think it's typically kind of scaled so that the numbers look like the Pauling numbers. And in fact, there are multiple other scales as well. So they're all kind of roughly similar, but not identical. And this is one of the reasons that electronegativity is just a kind of slightly vague, slightly slippery scale, because there's so many different ways of measuring it, and it's not quite as precise. You'd never get electronegativity to, you wouldn't look at it to 5 significant figures or anything in any kind of meaningful way. So it's just slightly vague. But as I say, overused. But I think we've looked at here in the last few slides different contexts in which the electronegativity scale does have good application. Having considered electronegativity as an atomic property, that's brought us on to the topic of dipoles, which actually led us to intermediate bonding. Because of course, when a covalent bond has a dipole, that's a covalent bond having some ionic character. And so having looked at intermediate bonding in this way, I thought it would be kind of consistent for completeness to look at it from the opposite direction. And that's when you look at ionic bonds and consider how they can have a bit of covalent character. And again, you can look at this as a kind of difference in electronegativity phenomenon. So if there's a very large difference in electronegativity, we'd be looking at something that's essentially pure ionic. And in fact, that diagram at the top right there, where you have these kind of spherical ions, these kind of perfect undistorted spheres, that kind of reflects, as it were, perfectly pure ionic bonding. So if you like cesium fluoride, this would be our example with the greatest electronegativity difference, and so our purest ionic bonding. That just really represents an extreme. But with other types of ionic bonding, we see a little bit of covalency creeping in there as well. We see some intermediate bonding. But now we're going to look at it from the kind of opposite point of view. And so really, we tend to focus on the cation here. So cesium plus that cation, which is giving us this pure ionic bonding in cesium fluoride, this has an extremely low charge density. So we can think of the charge density of an ion. It's the charge divided by the volume of the ion. So cesium, it's got the smallest possible charge of 1 plus of a cation, and it's also a large ion. Down there, we'll have in the 6th row of the periodic table, so a particularly low charge density for the cesium ion. But actually, when you start looking at metals which are slightly more electronegative than cesium, we see that the ions start becoming more charge dense. And a sort of fairly extreme example I've got here is aluminium 3 plus. So aluminium there, this is in the 2nd row of the periodic table, so certainly a smaller ion from that point of view. Plus it's 3 plus as well, so it's got 3 more protons and electrons, it's emptied its outer shell. Al3 plus is really quite a small cation, and it's got this big charge on it as well, 3 plus. So aluminium 3 plus is particularly charge dense. And so one thing we need to bear in mind with a very charge dense cation is that these are going to be polarizing for their neighborhood. With all that electric charge concentrated in a small volume of space, it's like quite an intense electric field around that ion. And so it means that electrons from a next door anion are going to get pulled across towards this intense electric field around the positive cation there. And so you can see on the diagram on the bottom right there, we can see that the anion there in the pink has got distorted or polarized, to use the technical term. So no longer is it just a perfectly regular sphere, but that electron density has been kind of dragged over there to the right towards the cation. So this is a polarized anion, and this actually reflects a degree of covalency. Because if you think in the kind of limit of this picture, once you start dragging more and more of that electron density over onto the cation side, it gets to the point where effectively that electron density is being shared between the two ions. And that's what we mean by covalency, the sharing of electron density. So this polarizing effect is effectively like a form of intermediate bonding. It's introducing a little bit of covalency into our ionic bonding. So it's intermediate bonding, kind of looking at it from the opposite direction, from the kind of ionic direction. So we've got these kind of, as I say, this kind of model form on the top right there, where you've got just a pure ionic interaction with no polarization whatsoever, and so we tend to consider these ions as perfectly spherical. And then the more charge dense cation, which we would call polarizing. Or if an ion is very charge dense, we can also say it's got high polarizing power. And so these cations are more electronegative than, for example, something like cesium, a very low charge density cation. So if you think about it, if a cation is going to have very low charge density, it's going to be large, so that puts it down low in the periodic table, and it's going to have a small charge, so that's going to sort of send it to the left-hand side. That's why cesium on the bottom left there of the periodic table is going to have the lowest charge density of an ion. Similarly, if you think about the anion, so fluoride, that's our most electronegative atom. So fluorine is the most electronegative atom. The fluoride ion there, again, this ion, it's holding on to its outer electrons very, very tightly. So another way of putting it is that the fluoride ion is not very polarizable. A polarizable anion would be an anion which is not holding on to its outer electrons very well. So, for example, if an anion was much larger, this could be the result of it being further down the periodic table. So as you go down the halogens, when you get to iodide, for example, that's a much larger anion, more shells of electrons. And likewise, if you've got a higher negative charge on the ion as well, that's also going to swell up the size of the ion, because that extra electron that you put on, it's going to repel the other electrons, and all this mutual repulsion will make the electrons move a little bit further away from each other, making the ion larger. And so as the non-metal ion is associated with an element that's less electronegative, then the ion will tend to be larger and more polarizable. So as the difference in electronegativity gets smaller between a metal and a non-metal, the metal is getting more charge dense probably, and so it's going to have greater polarizing power. And the non-metal, as it gets larger and possibly with a greater negative charge, is going to become more polarizable. And so the combination of a cation with high polarizing power and an anion that's very polarizable will lead to a great deal of polarization. And this polarization is the covalency that's creeping into the bonding. So of course, in the limit of the electronegativity values getting very, very close together, of course, it will have gone from, a certain degree of covalent character to being essentially covalent. And so this is when if you like, the ionic with covalent character will start turning into polar covalent, which is like covalent with ionic character. So it's a kind of sliding scale, as it were, where one just merges into the other. So there we go. I thought I'd add in this aspect of intermediate bonding, looking at it from the ionic direction there.